Okay, so there's a couple of ideas that you need to get out of this lab, and there's different formulas that represent different things. Okay, so one of them is what is a vector quantity and what is not a vector quantity. So you have two primary vector quantities. You have forces and you have electric fields. Both of those are vector quantities, which means you both have magnitude and they both have direction. Okay? So when you look at how you calculate voltage, okay, voltage is not a vector quantity, mainly because of the fact that you can think of voltage, like let's say for example, you have a positive charge, and this is where potential energy with charges gets weird, okay? And we're going to spend a lot more time talking about this, but this is where this gets weird. So if you have a mountain, okay, and you push something up the mountain, do you have to do work?
Oh yeah, force over distance.
Does the rock want to roll up the mountain?
No.
Hey,
So you have to do work to push it up the mountain, right? And it doesn't make any difference which side of the mountain that you're on. You have to do work. And you're building gravitational potential energy. And when you let go of it, what's the rock going to do?
it's gonna roll.
It's going to roll downhill because Mother Nature prefers kinetic energy over potential energy. Okay? Now, you got this. And work has to be involved. Now, if the rock is rolling down the hill, think this through. Would you have to do work to keep it from rolling down the hill?
Yeah.
Keep it from rolling.
Yes. Because it wants to roll down the hill. So you'd have to be pushing up the hill to keep the rock from rolling down the hill.
It's a lot of work.
Does that make sense? Okay.
That's too much work.
So in one situation, you push the rock up the hill and you're building energy. The other one, you're still pushing up the hill, but you're preventing it from rolling down. Got that visual? Okay. Now, you put a positive test charge here. So in the middle of this field, you have a positive charge, right?
Yeah.
Now, if you look at how you calculate voltage, voltage is equal to what? KQ over R.
Yeah.
Right? KQ over R. Look at the units. K has what units? Okay.
Newton meter squared over Coulomb squared.
Newton meter squared over Coulomb squared. Q is coulombs. R is going to be meters, right? So you lose one of those. You lose one of those. You get Newton meters over Coulomb. Well, Newton meters is the same thing as joules. So that's why voltage, another way to look at voltage is joules per coulomb. So if you go back to the rock that you're pushing up the hill, okay, you can think of that as almost like joules per kilogram, right? Because you're storing energy as you push that rock up the hill. And the bigger the rock is,
The more work.
the more work you have to do, the more potential energy that you store, right? Okay. So voltage is joules per coulomb. It's how much energy there is in that charge. Now you understand what the units are. That's important.
Yes.
Joules per coulomb. Voltage means joules per coulomb. I have a positive charge. I want to push a positive charge closer to it.
That'd be tough.
What?
If they want to.
They want
There you go, right?
Go away.
So you pushing a positive charge towards another positive charge is like pushing a rock up the hill. Okay? Now, you push these two positive charges together. You're increasing the potential energy. Because if I push them together and let go, what's it going to do?
Shoot away.
Oh, they're going to go flying apart. just like pushing a rock up the hill that you let go of it and it goes flying away. Now, if you push this really close
That's a lot.
and you let go,
Lots of.
this is analogous to stopping a rock from rolling down the hill because of the fact that it really wants to go flying away. So if you want to keep it from going too fast, you push in the opposite direction that it's going, much like keeping something from rolling down a hill. Okay. So if you have two positive charges, you have to do work to push them together. Now, if you have a positive and a negative charge,
They attract.
they attract.
They want to be with each other.
It's flipped. Okay? It's flipped. Because now you would have to push in this direction to keep it from going towards the positive charge. Okay? Or, the other side of it, if you push it in that direction, what are you building up?
Which direction?
If you push it away from the positive charge,
Potential energy.
you're building up that potential energy. Now, we'll get into this later. Up to this point, energy has always been a positive value, right? When you get into electrical fields, it can be positive or negative.
What?
Whoa.
That's
Yeah.
Why?
Just hold off on that thought. Just understand it for now.
Okay, sí, señor.
Okay. So, here's the whole point of all the questions that I'm asking on part 2, which is what you're going to delve into next. Okay? So, you're going to place a 1 nanocoulomb charge. So let's go back to this. You're going to place a, oh, not what I want. You can take 1 nanocoulomb charge, put that at one point, okay? And then you can take a negative 1 nanocoulomb charge 2 meters apart, okay? So you're going to have this action going. So you're going to have a positive and a negative. So here's what I want you to see, and this is the whole point. And this is the difference between voltage and electric field. So all the questions on part 2 is to get you to understand the difference between voltage and electric field. Let's start with the electric field part of this. Electric field, remember, how do you calculate electric field? That's one way. Okay?
Yes.
Right?
I knew it did something.
F equals.
KQR squared.
You can also do
Ed,
KQ over
R
R
squared.
squared.
R squared.
Ed.
Okay. Now, is the Q
Source.
the source or what you're testing in the field? The source. The source.
Ed, that's that.
So because this is charged, is it possible for your electric field to have a negative value?
C.
It can also be a positive value.
No
because
way.
it's the source charge. Okay? Now, remember, the direction of the electric field is based upon a positive test charge put in that field. Okay? So the direction of the electric field is based upon what a positive test charge would feel. So if I go back to this program, and this is an electric field sensor, okay? And if I put that right there, notice that that electric field is pointing towards that negative charge. Because if you put a positive test charge right there, it's going to feel attractive toward that negative value. But if I take that same thing and I put it on the opposite side by the positive, it points away from it.
Yeah.
Because a positive test charge in that field would feel repulsion. Okay? So this is what I want you to see. Electric fields are vector quantities because it's got like negative 141.3 deg. And what are degs? Degrees. Okay? Not that anyone asked that question, I'm just saying. Okay? So those are degrees, all right? So if I just have a positive charge and I put that right there, I know that if I just have a single positive charge, that electric field is going to be pushed in that direction. But if I put a negative charge over there, why won't that cancel out? Beautiful. So in between these, there's no way for me to have a zero electric field in between a positive and a negative charge, because they're going to get pushed from one and pulled from the other. Now, voltage though, voltage is not a vector quantity.
C.
So when you do your voltages, which are K, and then you can get a sum of these, KQ1 over R1 plus Q2 over R2. Now, is it possible to have zero voltage?
Yeah.
Yes. Now, if I go back to this program and I try and measure that voltage like in between these points, yeah, pretty close. Okay. So here's the dichotomy between if you have opposite charges. You cannot have an electric field that goes to zero in between two oppositely charged particles, because the electric field is a vector quantity. So it gets pulled from one and pushed to the other. But your voltages are sums of the charges. So since this is the overall voltage. Now, here's the other way that you can view this in terms of voltage. Because voltage is joules per coulomb. Now, stay with me here through what I'm about to say. Okay? A lot of times when you talk about voltage and energy with electric fields, you're basing upon what happened if it was infinitely far away, and it was infinitely far away, and you push it towards a particular charge. So imagine that you have a positive and negative charge, which is what you have here. And I have an electron that's infinitely far away, or a proton, doesn't make any difference. Let's say it's positive to be consistent. So imagine that I have a positive charge infinitely far away. So what that means, that positive charge infinitely far away, if I were to push it to be in between these points, I don't have any net resistance. Because yes, the positive charge, if I stayed right in the middle, it would always kind of be repulsed by that positive charge off to my left, and it would always be like attracted to the positive charge on the right. As long as those two charges were the same, all I have to do was keep it right in the middle, okay? Because it's going to feel an equal repulsion and attraction between those points. So if that positive charge was infinitely far away, I wouldn't really have to do any work to get it in between those points, because it's always going to feel a repulsion and attraction. Now, however, if I swap that out and I put another positive charge over here, now imagine this. I have a positive charge that's infinitely far away, and I'm going to try and push it in between those two positive charges. Is that going to take a lot of work? Yes, because of the fact that I've got to push this thing in between two positive charges that don't like each other. So if I push that thing in between those two positive charges, that's going to build up a lot of energy per unit of charge, because I'm pushing it from an infinite far away distance to be between two positive charges. And that's going to take a lot of work. So that's going to build up a lot of energy. So if I go over here and I take that voltmeter and I put that in between, that's like 14.2. So notice that that's a positive value, because it's the sum is KQ1 over R. Now, if I swap these out, and I put two negative values there, now what happens to the voltage? Negative value. So voltage could be positive or negative depending upon the charge. Now, the reason that it's negative, think this through. Again, I have a positive charge that's infinitely far away. If I let go of that proton, that positive charge, what would it do? It would go screaming towards these two negative charges. It's like, hallelujah, I have found my people. Okay? So you're keeping it away from it. So you have to exert a force to keep it from going in that direction because it wants to go in that direction. Okay? So that's why that's a negative value. Okay? Does that make sense?
I see.
I see, said the blind man.
2 is,
So-
2 is death why.
When you're answering questions 12 and 13, okay? And this is the whole point of this, leading up to questions 12 and 13. So if there are two positive charges, can the electric field be zero? Can the voltage be zero? Explain. You need to address both aspects of that question. Can the electric field be zero? Yes or no? Explain why.
No.
Can the voltage be zero? Yes or no?
No.
Explain why. Then if you have a positive and negative charge, can the E field be zero? Yes or no? Explain why. Can the voltage be zero? Yes or no? Explain why. So I'm going to stop talking for a while, work on part 2.